Okay, we're going to continue on here, chapter 13. So last time we talked about acids and bases, and we talked about a couple of or a bunch of calculations. So we talked about Kw, which is the concentration of H plus times the concentration of OH minus, and that equals 1 times 10 to the minus 14. This is basically like your acid part of your solution, your base part of your solution. And you could obviously use this, as we talked about, as really a constant value, even though it does change with temperature. But for the most part, and probably 99.9% of the time, it's going to be pretty much that number. And you could compare the H plus concentration to the OH minus concentration. And if they are equal to each other, then you have a neutral solution. If your H plus concentration is larger than your OH minus, then it's acidic. If the H plus concentration is less than the OH minus, then it is basic. We talked about the pH scale. Again, goes from 0 to 7 to 14. Acidic there below 7, basic above 7, and really neutral there at 7. Remember that the relationship between H plus and OH minus is an opposite relationship. As one goes up, the other goes down, so they kind of go in opposite directions. 7 going towards 0, again, going to be more acidic. And obviously, if you're heading from 7 towards 14, it can become more basic in that case. You calculate the pH by taking negative log of the H plus concentration. Remember, we also talked about your calculator, and depending on what type of calculator, as to making sure that you do punch it in correctly. Again, a display calculator, just the way the formula is written is how you punch it into the calculator. If you have a non-display calculator, you got to kind of work backwards, usually starting with the number. We saw a similar type of scale, which is POH, and it does measure the OH minus versus this guy that measures the H plus, and that's minus the log of the OH minus concentration. A nice relationship between the two, pH plus POH equals 14. So it does give you some options. You can obviously, if you have, like I said before, the OH minus concentration, but want the pH, you can very easily just get the POH and subtract 14. You'll have your pH pretty quickly. So it's a good kind of move. We also can, as we talked about, directly from the pH, get the H plus concentration, and that is our inverse log of the negative pH. Again, as we talked about on most people's calculator, when you do that inverse log, it usually will pop up a 10 and a caret. To get to the inverse log on most people's calculators, upper left corner, shift, second button, and log button is usually what you have to hit there. Same thing with the POH. Once again, you can directly from the POH get the OH minus concentration. It's actually the same calculation, obviously the inverse log of the minus POH. That's going to give you a 10 and a minus POH on that case. So it does give you a variety of ways to do it. You can actually just, in a lot of cases, avoid KW and just kind of go with the last route here to get to everything. You can still use KW if you want to get concentration. So it all should work out the same. We also talked about the pH of a strong acid or base. And if you have a strong acid or base, really for the acid, what you're interested in is the H plus concentration. For the base, what you're interested in is the OH minus concentration, because that will get you to the POH, and then you could get to the pH. That obviously will get you right to the pH. Remember that, as we talked about, there's kind of 6 really strong acids, and those are good ones to know, because again, at like a process of elimination, if it's not one of those 6, it's probably going to be a weak, which means you'll have to do some different type of calculation. Bases as well. Remember, most of our strong bases, group 1 and 2 from the periodic table, that has OH in the formula, like sodium hydroxide, potassium hydroxide, barium hydroxide. Those are all strong bases. Also, out of the 2, as we talked about there at the end, probably the base would be the one where you might have to adjust the concentration. So like we did in that example, I think we had barium hydroxide. When it broke apart, you got 2 hydroxides, right, for every one of the barium hydroxide. So you did have to adjust the concentration to get the proper hydroxide concentration before you went into the POH. So just remember, keep that in mind. Any questions on any of that stuff there? We talked about it last time. All right, so we obviously talked about strong, so why not talk about weak, I suppose? So let's talk about what happens with weak acids. And in a weak acid, because it is a weak electrolyte, like we talked about, it will do a reversible reaction, which means it will set up an equilibrium. So if this is a weak acid, it's going to set up an equilibrium. And because it will do that, you could set up an equilibrium constant, just like we've done previously, products over reactants here. And not surprisingly enough, this is known as a Ka value. And the Ka value added to our list of Ks, so we got Kc, Kp, Kw, now Ka. It just keeps growing. That is what is sometimes referred to as the acid ionization constant for a weak acid. The relationship here is this: as the Ka value increases, the strength of the weak acid also increases. So let's see why that would be. A Ka value, a Kc value, a Kp value, they're all basically equilibrium expressions. And we know that if we have a large value for K, that means we should mainly have reactants or products. If we have a large value for K, we should have. It's the part where you insert the answer. Yes, you should have products, right? So large value of K means we have products. And in this case, if we had a large Ka value, we would mainly have products. And that would mean that we would mainly have H pluses that have been released into the solution free. And that's your definition of an acid, right? So it's the ability to release that H plus. So when we have a large value of Ka, it's considered a strong weak acid. It is still way weaker than a strong acid. But when you're comparing a weak acid to another weak acid, you can look at the Ka value. And again, the larger Ka value would be a stronger weak acid. Again, something like HCl would be much stronger acid than any type of weak acid that you would have. Now, do I have Ka values for something like a strong acid? Does a strong acid have a Ka value? The answer is no, right? Because the difference between a strong acid and a weak acid is a strong acid is a one-way street, right? There's going to 100% dump out on the product side. There's nobody going back, so it will not set up an equilibrium. So we do not see Ka values for strong acids. The one exception would be sulfuric acid because it's a diprotic acid. But if you ever look up the value for the Ka value for sulfuric acid, in most tables it says large, which is not a very helpful number, right? So, but we typically do not have Ka values for strong acids because they do not set up an equilibrium. So that is a very big clue as you're working through problems. If you see a Ka value, it's a weak acid, yeah? So you don't have to worry about it. So that's another piece of information along with those 6 strong acids to help point you in the right direction as you go through these problems. So see a Ka value, definitely a weak acid involved. And because it's a weak acid, and here's a table similar to the ones you have in your book of the Ka values, similar to how we work equilibrium problems is how we work sort of weak acid problems. So unlike a strong acid where really because it's going to completely break apart and that will give you your H plus, you could go right into the pH equation. Because this is a weak acid, it's going to set up an equilibrium. You actually have to do an equilibrium problem to figure out the pH for a weak acid. And the main difference between, say, a normal equilibrium problem and a weak acid equilibrium problem is what you do at the end. And at the end of these type of problems, we're not necessarily usually interested in everybody's concentration or pressure. We're interested really in the concentration of H plus so that we could then put it into the pH equation. So with a weak acid, you have to kind of do an equilibrium problem in the middle. And then afterwards, use that H plus concentration to go into the pH equation our formula. With a strong acid, because it completely breaks apart, you don't need the ice table part of it. You go right into it. So that's the main difference here between them. You can solve these just like you could solve any equilibrium ice table problem, which for our purposes, perfect square, right? Quadratic, or you can still do the assumption just like normal. I would say probably in most cases with weak acids and kind of beyond that first chapter, very rarely will you hit a perfect square on this deal. So it's probably going to be either an assumption or a quadratic is sort of how you would probably solve most of these sort of problems. So let's go through this one here and see what we get. So HF has a Ka value of 6.4 times 10 to the minus 4. So the first thing I know, first off, is HF is not one of those 6 acids, but I don't even really have to think about that because as soon as I see this thing, I know it's weak. Yeah. And as soon as I see it's weak, I should then think about getting a nice cup of ice, yes, and doing a nice table here and to solve these. So these are the things you want to think about as you kind of go through the problem. And at this point, it really is just an equilibrium problem. Now, this is the point where you can choose whichever way you want to do it. As I mentioned before, since this is a weak acid, it is going to dissociate in water. And I personally do not use water in my reaction. And if you want to, you can use water. And the only difference here is you would have water on the left over here, and instead of H plus, you would have H3O plus. So again, if you want to use that, it's perfectly fine. But I personally don't do it. But again, you could do it that way if you like to. And we're going to do our ice table. So we initially here have our 0.5. We got 0 and 0. Normally here, we're going to assume it's going to the right because we have no product. So minus x, and plus x. And at equilibrium here, 0.5 minus x, and x. First off, any questions on the ice table? Yeah. I would say if you're not asked to solve for the Ka, yeah, you would probably be given either in the problem or it would be in a table. And for the book, you may have to go to the table to look up some K. Yeah, very commonly don't. They just assume that you'll go look up in a table. So my answer probably for the book would be you definitely has to probably look it up in a table. On an exam or quiz, it will probably be there somewhere, either in the problem or in a table if you need it and stuff like that. But definitely. And that also, when you work out, for example, problems in the book, knowing those 6 strong acids, if you come to a problem and you see it's an acid, it's not one of those, then you know you should go and look it up in that thing, even if it didn't say it was like a weak acid or something like that. No. Now, a reminder that in this class, right, you do need to write the reaction, yeah? So you can't just fake the calculation like a lot of people like to do and go like, I know there's some X's and stuff like that. So you need to show all that stuff, yeah, as you're doing it for full credit. We could write our Ka expression here, which would be H plus times F minus divided by HF, and this is going to equal 6.4 times 10 to the minus 4. Again, if you'd use the H3O plus in the water would not be included, right? Because it is a liquid, and the H3O plus would just basically take the place of H plus there in the expression. Like a normal equilibrium, we're just going to take our equilibrium line, right, and throw it in there, and we're going to solve for x. So if I do that, it's basically going to give me x squared divided by 0.5 minus x equals 6.4 times 10 to the minus 4. At this point, we could solve it. Again, you do have options. This is not a perfect square, so you cannot square root both sides, by the way. You could quadratic it if you want, or we can remember from last chapter, right? That is considered a small value of K, right? And that means that we can try the assumption if you want, and we could assume X is equal to 0 in this case. And if we assume X is equal to 0, remember it is really just the X's you're going to subtract from a number or add to a number. Those are the ones you want to get rid of. So that's going to give you X squared divided by 0.5. Equals 6.4 times 10 to the minus 4. I'm going to multiply this to the other side. I am then going to square root it afterwards, just kind of do one after the other. So we're going to go 6.4 to the minus 4 times 0.5, and we'll do a little square root action on it. And that's going to get me an X value of 0.01789, we'll call it. Remember, as we talked about previously, if you do an assumption, you do need to check your assumption to make sure that it is okay to do. We are following, again, that 5% rule. So basically what you're going to do to check it is you're going to take the X value you just got, you're going to divide it by the initial concentration, which is essentially what you're going to subtract it from. And you're going to times it by 100% in this case. And you end up with like 3.6%, which is less than 5, which means the check here is good, right? Now, for our purposes here, that is essentially what we are looking for, because we are interested in the H plus concentration, because ultimately we want to get the pH. So in this case, we could throw a molarity on that if you want, and that would actually equal the H plus concentration. Now that we have the H plus concentration, now we could go into our pH equation at this point. And we'll go with minus the log of what we got there, 0.01789. I'm just going to use the whole number. I think that's still in my calculator here. Should be it. And that's going to give us something like a pH of 1.7 in this particular case. And it is acidic, which is good since this is an acid. Again, if you ended up with a basic pH, you probably screwed up somewhere along the way, I would imagine. Now, if you wanted to quadratic it, you could, and you should technically get the same answer. So if you want to take that route, you could. Any questions on that there? So weak acid problems takes a little bit more work. It requires an ice table and an equilibrium calculation. Again, the goal here usually is just get that H plus concentration so you can get the pH. All right. Now, again, just a reminder, as we talked about, if you did this exact same problem, except that your concentration was different, for example, if we had HF going to our H plus and our F minus, and what was that? It was 6.4 to minus 4. And let's say in this case, we had what we have down there, instead of 0.5 molar, we have 0.5 molar as our initial. So we would do our ice table like we just did, minus X plus X plus X, 0.05 minus X, X, and X. Just like we did on the previous slide there, this would go into our expression, X squared, 0.05 minus X equals 6.4 times 10 to the minus 4. We will assume X is equal to 0 here. Gives us X squared divided by 0.05 equals 6.4 times 10 to the minus 4. Once again, we're going to multiply and then square root. And if we do that in this case here, we will end up with this as our X value. We will end up with something like an X is equal to 0.005657. Now, when we divide this by our concentration, we're going to subtract it from 0.05 and times it by 100%. We now get something closer to 11.3%, which gives us a sad face and not a good assumption. So in this case, we would then have to go back and solve it another way. For our purposes, probably you'd have to go back and do the quadratic. So again, you should always check it. Sometimes people get in the habit of not checking, just kind of assume it's going to always work. It will not always work. Something we'll talk about here in this chapter is obviously concentration is the difference here, right? And just the quick answer as to why it doesn't work is this. I like to use a pizza example, right? So if you have a whole pizza and you take one piece out, not a big deal, right? It's a small little bit. It's going to be okay. That would be like your 0.5 molar there. Now we go to 0.05 molar, which is, much less. if you had now that same pizza, but you only had two pieces left and you took a piece out, you just took 50% of the pizza, right? Because nobody ever takes the last piece, right? Everybody just walks by it and goes, "Nah, I can't take the last piece," right? But if you only started with a smaller amount, when you lose something that's even small, it is a bigger proportion of what you started with than if you had a much larger starting amount and you took a same small piece out of it. So that's why, again, sometimes the assumptions may work or not work. The initial concentration is important. And also the equilibrium constant value is also an important factor as to whether or not it will work. So again, just a reminder, make sure you do check. Any questions on that there? Yeah. It is 5%, yeah. So anything kind of less than 5%, you're pretty much good. And then anything kind of above 5%, you do have to kind of go the other way. Now, in certain cases, depending on where you're at with the concentrations and stuff like that, you may find that if you did the assumption and it was bad, and then you went and actually did the quadratic, you'll end up with a number very close to what you would have got with the assumption. But it won't always be that way. It just kind of depends. For example, if you did it and it was like 5 point something percent, and you then went back and did quadratic, you're going to have a number pretty close to what you got. But we are going to go with the 5% rule. And again, if it's over 5%, you do have to kind of go back and do it another way. Other questions? All right. So as we just saw there, we do weak acid problems, just like we do regular equilibrium problems. And again, the main difference is at the end here, you're probably going to go into the pH equation. And you will be interested really in the H plus. Now, one of the things that you sometimes do come across that we will not do in this class, and then most people don't really take it into account, but books like to do it sometimes or take it into account, is what it says up there on the first one. We, in most cases, will ignore the autoionization of water. And what that means is everything that affects the pH of that solution, all the H plus, for example, in our calculations, we assume come only from the acid. Now, as we talked about earlier, right, water will react with water, right, and have a certain H plus concentration and OH minus concentrations. Now, some books will, and especially in like solution guides and stuff like that, sometimes they'll go, well, your H plus concentration is so low, the native concentration of water, so H plus concentration, is much larger. So that's going to be sort of the contributor to the pH of that solution. So we don't worry about water's contribution. Everything that affects it either came from the acid or base that's there. So you don't have to worry about that. But I say that because I've seen a lot of textbooks where they kind of solve problems that way and they go, well, and everything ends up being, well, water's much larger of a value than, what you have there. So all the answers end up being kind of like the same in water's sort of contribution. So we will not worry about water's contribution to the pH. It will always come from just the acid or base when you do it. All right, so why don't you give it a try here. What's the pH of a 0.122 monoprotic acid who has a Ka value of 5.7 times 10 to the minus 4? Monoprotic means it could give away one hydrogen. And if you need a formula to use, this right here could be used as a monoprotic acid. Okay, so let's take a look to see how you're doing. Again, this is a monoprotic acid. Once again, this is a big hint, yes, that this is a weak acid. And again, as we talked about a second ago, that should direct you to, I should do an ice table, right? So pretty much in this class, that's a safe bet almost on a lot of things. Go for an ice table if you're not sure. We needed the equation. So again, this is just going to be a weak acid that's going to dissociate in water. Once again, I'm not going to include the water, but you're more than welcome to do so. And the only difference, once again, is you'll have the water on the left, which would be a liquid, and H3O plus on the right. That will give us our Ka expression, which is our products over our reactants here. And that's going to equal our 5.7 times 10 to the minus 4. At this point, it really just turns into just a basic equilibrium ice table problem. So we're going to go 0.122. Like normal, obviously nothing mentioned on the right-hand side. So like we've been doing, safe to assume that it's 0. Because of that as well, our kind of assumption that should be okay in this case, we're reaction should be heading towards the product side, which means we should have our minuses over here and our pluses, x's on this side. That's going to give you here 0.122 minus x, x, and x. Any question on the table here? So we're going to go obviously into our expression here. That's going to give us x squared divided by 0.122 minus x equals 5.7 times 10 to the minus 4. That is a small value of k, so you can assume x is equal to 0, but because you are professionals, you know that's 6.8% and not a good outcome in terms of that, right? So you get the unhappy face happening here. So if you did the assumption, hopefully you checked it because you would see it's 6.8% and it's too high. So we do have to solve it another way. So that's going to be quadratic in this case. So I'm going to multiply everybody that side to kind of get everybody into the right spot I need. That should give me x squared is equal to 0.0000695 minus 5.7 times 10 to the minus 4x. Obviously here I need to bring everybody back to the other side to get everybody on the same side of the equal. And that's going to give me an x squared, going to give me a plus 5.7 times 10 to the minus 4x minus 0.0000. I guess I could have scientific notation that there, and 0. That's going to give us our quadratic, right? Our a, b, and remember, you do need to take the negative here with the c when you go into it. So we're going to go into our x is equal to minus b, so that's minus 5.7 times 10 to the minus 4 plus or minus the square root, right? And again, it is x is equal to minus b plus or minus square root of b squared minus 4ac divided by 2a. If you do everything inside the parenthesis or the square root there, you end up with 0.000278485. If you then square root it, 0.01669 looks like. See what you get there. And that's all going to be divided by 2 times a, which in this case is actually just 2 in this case. If we do our plus first, so take the minus 5.7 times 10 to the minus 4 plus our 0.01669, 69. That's going to give us an x value of 0.00806. If we do the minus part, so minus 5.7 times 10 to the minus 4 minus 0.01669 divided by 2, gonna get us a negative 0.00863. Clearly, we're interested in the pH, which we could see from our ice table is equal to X. That clearly means we cannot have a negative number, right? Or a negative concentration, so that would not be the good one. That means this one here is gonna win for our H plus concentration. And now we have our H plus concentration. We're ready to go into our pH. So our pH is equal to minus the log of the H plus, and that's going to get you minus the log of what we got there, 0.00806 and 2.09 maybe. 0.806, 2.09 looks like winner. I'll go down here, 2.09, which is acidic in this case, and the correct answer. Any questions on any of those steps? So as you can hopefully see, it really is just the same calculation, just sort of a different application there at the end, and in a lot of cases using the pH equation with it. Any questions? All right, I think it's actually a good place to start.